In section 11.3, we're going to look at some more tests to use to determine if series converge or diverge. First, a definition. A non-negative series is one in which all terms are greater than or equal to 0. So it can be 0 or positive, but not negative. So here we have a basic comparison test. And if you remember, we had a comparison test for improper integrals. This is the exact same idea, but for series. There's a lot of parallels and connections between series and improper integrals. Consider two series, one being the sum of the a sub k's and one being the sum of the b sub k's. And this inequality establishes that each of the a sub k terms is in fact smaller than its corresponding term in the series b sub k, and all of these terms are going to be bigger than or equal to 0. If the series based on b sub k converges, meaning the series with the larger terms, then so does the series based on a sub k. And specifically, the series based on a sub k will have a sum that's less than or equal to the sum of the series based on b sub k. And if the series based on the smaller terms, a sub k, diverges, then so will the series based on b sub k. So again, these ideas are exactly analogous to what we saw with improper integrals. In example 1, I'm looking to determine, does the series, as k goes from 0 to infinity, of 1 over 2k plus 1 converge? I'm going to bring back something that we looked at in a previous section, which was we looked at the series where k goes from 0 to infinity of 1 over 2 to the k power. So the first couple terms of that are 1 over 2 to the 0, which is 1, plus 1 over 2 to the first, which is a half, then a fourth, etc. We proved that this series would converge to the number 2. And the reason, obviously, that I'm bringing this one up is the comparison test. You, again, compare one series that you know the behavior of with one that you don't. The first thing we need to determine is which of these series is actually the one with the larger terms. So you can take a look at a couple of the terms from each of these series. I'll write out the first couple of terms for this series here, where we would have 1 over 1 plus 1, so 1/2 would be the first term. Then we'd have 1 over 2 plus 1, so we'd have 3. Then we'd have 1 over 4 plus 1, so we have a fifth, and so forth. If we compare the corresponding terms, the ones that were generated by the same k values, notice what we see. The first term here is 1, which is larger than the term in our series. The second term is again larger than the second term of our other series, and so forth. So what this establishes for us is that, in fact, this series that we've already proven the convergence of is larger than the one that we're looking at right now, and that our terms are all positive or equal to 0. And now we have satisfied this condition of the comparison test. So in this particular case, this series would represent b sub k, and the series based on this one is the a sub k mentioned in the comparison test. So the comparison test says if our series based on b sub k, which is this one, converges, then so does the series based on a sub k. So I would say something along the lines of, since we know the series based on 1 over 2 to the k power converges, so does the series based on 1 over 2 to the k plus 1. Now, in addition, there's this extra condition here. Once you've established the convergence, What you converge to is going to be smaller than or equal to what your comparison series converge to. So the last thought we can add here is we can say it will converge to a value less than or equal to 2. And that should make sense because if you remember looking at the convergence of a series as the limit of the partial sums, if all of the numbers in this first series are bigger than all the numbers in the second series, all the partial sums here are also going to be larger than the partial sums of the series we're interested in. The comparison test actually leads to this test, the integral test for positive series. So we're going to be bringing integration back into the mix. Suppose that for all x greater than or equal to 1, the function a of x. So now we're kind of going back to comparing a series, which is made up of discrete terms, to a function that is positive, continuous, and decreasing. You've got to verify that all of these 3 conditions are true. Then you can compare the series based on k taking on values from 1 to infinity to the integral with limits of 1 to infinity for the function a of x. And here's that connection between the series notation and the function. So a sub k is going to be the same as a of k for integers k greater than or equal to 1. And the important conclusion is if either one of these diverges, so does the other. And if either one converges, so does the other. So the series will have the same behavior as the related improper integral. And using this as a formula, we can establish a lower and an upper bound on the value that the series will converge to. In order to be able to use the integral test, you're going to have to be able to employ integration techniques, and you're going to need to remember how we evaluated improper integrals. So you may want to go back and refer to those notes. Suppose I want to know if the series where k goes from 1 to infinity of 1 over 10 times k plus 1 converges. What I would initially do is I would look at the expression that the series is based on. And this is something that would be relatively easy to integrate. It would involve a u substitution, but it's certainly not difficult compared to other things that we've seen. I can say, all right, I'm going to let my function a of x be the function based on that expression. This needs to be true for x greater than or equal to 1 because that's what our index of summation tells us. And what I need to check are the 3 conditions that this function on this interval will be positive, continuous, and decreasing. Positive is relatively easy to think about. If you're going to be plugging in x values bigger than or equal to 1 into this fraction, you should be able to convince yourself pretty easily that the outputs will be positive. It's going to be continuous because the only problem you ever run into with functions based on fractions is where the denominator would equal 0. And if we take 10x plus 1, set it equal to 0, and solve for x, the only x value that's problematic here is negative 1/10, which is not part of this interval. So it's going to be continuous. And you can determine it's decreasing, obviously, by writing out a bunch of terms. There's also another way to do it, which is using the first derivative test, which you learned in Calc 1. First derivative test meaning if you take the first derivative, and the first derivative is negative on this interval, then you know that the original function is decreasing. We do have the ability to look at a graph, so figuring out that this is a decreasing function can be nice and quick. So here's the function that we're talking about, and you can see on the interval where x is a value that's bigger than or equal to 1, the y values, the outputs, are in fact decreasing. So once again, we've now shown that the values are positive because they're above the x-axis. This is continuous. We don't have any discontinuities, and this is a decreasing function. You do need to verify that these conditions hold. So this function is positive, continuous, and decreasing. If it isn't one of those three, or multiple of them, then you can't use the integral test. So now the integral test says we're going to compare the series that we're interested in to the integral from 1 to infinity of our function a of x, which is 1 over 10x plus 1 dx. This is an improper integral because the upper limit is infinity, and we know how to evaluate improper integrals. Remember, we do that by substituting the letter t for the value that is improper, and then we take the limit. So we're going to compare to this improper integral, and this improper integral we're going to evaluate by taking the limit as t goes to the value it replaces, which is going to be this infinity, of the integral 1 to t of 1 over 10x plus 1 dx. So the first step is to actually just evaluate the integral, then we go ahead and take its limit. So down here, I'm going to come up with a way to integrate 1 to t, 1 over 10x plus 1 dx. And a simple u substitution here will do the job, where we let u be the denominator of the fraction. We take the derivative of u. The derivative of 10x is 10. Remember, constant goes to 0, and then we always put a dx. And then remember, the last thing is we move that constant over to the other side in the form of a fraction. And we've completed our u substitution steps. We now would write this integral as a u integral, which would be 1 over 10x plus 1 is u, and dx we're replacing with 1/10 du. 1/10 goes in front, du goes at the end. I'm dropping my limits of integration temporarily because those only apply to the integral in terms of x, while I go ahead and take the antiderivative here. So I keep my constant. 1 over u is the natural log of the absolute value of u. The last thing I do there is now substitute u back so that I get an answer in terms of x, namely u is 10x plus 1. And I am going to be able to drop these absolute value bars because since we're considering x being greater than or equal to 1, this will never take on a negative value. So I can simply write my antiderivative as this. Now I can bring back my limits of integration because my antiderivative is in terms of x. So I just need to evaluate from 1 to t using fundamental theorem of calculus. That says I'm going to substitute t for x first all the way through, minus, and substitute 1 for x. So I have 1/10 natural log of 10t plus 1 minus 1/10 natural log of the number 11. That's as simplified as I can make this unless I employ some log properties here. So I'm now going to go back to where I left my comparison, and I said after I evaluate the improper integral, I need to take the limit as t goes to infinity. So I'm taking the limit as t goes to infinity of this expression here. And what I need to do is figure out, as t gets larger and larger, what happens to each of these terms. To help us do that, we can look at a graph. So I've entered the first term in as a function, and I'm looking for the limit as t goes to infinity. So what we can observe here is that as the x values or the t values are getting larger, the corresponding outputs are in fact getting larger also, although at a very slow rate. So the question is this going to level off and become horizontal, in which case it converges to a number, or does it keep increasing without bound and therefore it's heading towards infinity? If we zoom out, it gets to be difficult to tell whether this really is leveling off or continuing to increase. So what we can do is we can put in values for t, such as I can evaluate t at 100, then maybe at 1,000, 10,000, 100,000, and you can see that the outputs are continuing to climb, and it does not appear that they're reaching any particular value. The limit as t goes to infinity of this term is infinity. So we've just shown that this term is going to head towards infinity. This term is a constant. This is just a number. It's a relatively ugly number gotten by taking 1 divided by 10 multiplied by the natural log of 11. You'll get a decimal of approximately 0.240, we'll say. So overall, if we have a limit where one term goes to infinity and we subtract some finite value, the overall limit is heading to infinity. So going back to our integral test, if either one diverges, so does the other. We've just shown that our improper integral diverges, goes to infinity. Therefore, we know our series that corresponds to that improper integral also diverges to infinity. That's how we would wrap up this problem. Let's take a look at a second example. We want to know if this series converges. Now, again, if we're going to use the integral test, the improper integral that we form from this series would need to be one that's relatively easy to integrate. And 1 over k square root of k is not difficult as far as the integration goes. But before we can actually go ahead and perform that integration, we have to say, all right, so my improper integral is going to be based on the function 1 over x square root of x for x being greater than or equal to 1. And we need to confirm that this function is positive. Again, that's pretty easy to think about. Let x be a number bigger than or equal to 1. This fraction stays positive. It's going to be continuous because the only value that will cause problems here is when x is 0, which is not part of our interval. And again, the last thing you have to determine is if this is a decreasing function, which the fastest way again would be to look at the graph. Here's what the graph of our function looks like, and again, with a little bit of effort, you can convince yourself that the outputs of this function are decreasing in value. Now that we've verified that those conditions in order to use the integral test have been satisfied, we can write the integral that we're going to compare our series to. In this case, we're going to compare it to the integral from 1 to infinity of 1 over x square root of x dx. And because that's an improper integral, really what we're going to do is take the limit as t approaches infinity of the integral from 1 to t. So, like you saw before, the first thing that we'll do is work on the integral, get it down to an expression in terms of t, and then we'll be able to look at the limit. As usual, it's always helpful to get the radical expression out of your integrand and replace it with the fractional exponent that corresponds to it. And you can see I've also put an exponent on the x in front of it, just x to the first power. I'm doing that just to make clear what the next step is going to be, which is when you have things with the same base that are being multiplied, you can add their exponents together. So my integrand now becomes 1 over x to the 3/2 power dx. And hopefully you're familiar enough with negative exponents to realize the other way that I could write that is as x to the negative 3 over 2 power dx. This is now a simple case of applying the power rule for integrals, which says the antiderivative will be formed by adding 1, or in this case 2 over 2 to the exponent, giving me a new exponent of negative 1/2. And then I should divide by that new exponent or multiply by its reciprocal. So there's my antiderivative, which I need to evaluate from 1 to t. And before I do that, again, I'll just make this a little nicer looking. Negative 2 over 1 reduces to negative 2, and x to the negative 1/2 power is really a square root in the bottom part of a fraction. So the simplified form of this antiderivative is that it's the same as negative 2 over square root of x. Next, we apply our fundamental theorem of calculus. So we have negative 2 over the square root of t minus negative 2 over square root of 1. And with a little bit more cleanup, we're left with the expression negative 2 over square root of t plus 2. I can now go back and apply my limit as t goes to infinity to this expression. And again, I need to determine as t gets bigger and bigger what happens here. The limit of a constant is that constant, so this second term just goes to 2. As t gets bigger and bigger and goes to infinity, so t starts out small, like 1 or 4, then it gets bigger to 10, 100, 1,000, a million, this whole fraction is going to head towards 0. And if you can reason that out, great. If not, you can go look at the graph. But what I've just shown is that the limit then for this improper integral is 2. So since the improper integral is equal to a finite number, the series that we are comparing it with will converge. And again, that's based on the integral test. The series behaves the same way the improper integral does. Now, we're ready to use the second part of the integral test. So we said if either one of these converges, so does the other. And here's a formula that you can use to bound the series, give it a lower limit and an upper limit for what the value that it will converge to will be. Now on the left, you can see is the value of your improper integral, which we just calculated in our case to be 2. The series will converge to a value bigger than or equal to 2, but less than, and notice on the right here, you have the improper integral again, which we know is 2. And all we do to that is add the first term of the series. So as we just saw, the inequality will be the value of the improper integral is going to be less than or equal to the series value, which will be less than or equal to a sub 1 plus the improper integral's value. So all we have to do is calculate a sub 1 for this series, which if it's 1 over k times the square root of k, that's just going to be 1. So I now substitute 1 where the a sub 1 is, and I know that my series is going to converge to some number between 2 and 3, again, possibly being equal to 2 and possibly being equal to 3. So the integral test not only confirms the convergence or divergence, but if it does converge, will give you an idea of what the value that the series converges to will be.